working on the first part, this part, composite background, and also the review of stress strain, things like that. We are going to something called a micromechanics next, starting this lecture, and which really is talking about small things, how the fiber volume fraction fiber property, matrix property can factor into the lamina property. Basically allow you to estimate, based on the constitution, what the layer property is, which the property of lamina goes into the CLT. We come back to the micromechanic analysis number 4, which is a laminate theory, it's a plate theory. And then we write a code based on number 4. We started writing our code, laminate analysis. And then we use that code to do some failure analysis. So that's the progress. So we're pretty much in between point 2 and 3 at this point. Okay. All right. So we talk about these stress strain relationship. There are a wide variety of it. What's really concerning us that we use very frequently for composite is this single layer properties. So this is what's most important to us. It is under the state of a plane stress, and if you assume the material is has symmetry, like isotropic or transverse isotropic, in-plane stress is related to in-plane stress. In-plane strain is related to in-plane stress by this relationship. Okay, and this relationship has many forms. Usually, it's in this form when you have 1, 2 axis being the axis of symmetry, meaning that could be 1 is fiber direction, 2 is transverse direction. Then the matrix is simple. You have zeros. If you look at the other coordinates. This is the material coordinates. Now, if your material goes 1, 2 direction, 1 and 2 direction, that's your plane of symmetry. But you have to analyze the plate in XY direction, then you break the symmetry. And we have tools to transverse that. Your relationship now become this. So you can transform your stress from 1, 2 to XY coordinates through the matrix T. Okay. Similarly, you can transfer your strain. Strain can be related. The XY coordinate strain and the 1, 2 coordinate strain. We learned these. These are NTSN. You do NTSN transformation, you simplify, you get this. Okay. And then here is the basically this is the what you need to do when you write your code. So if you have your material matrix is S is in your 1, 2 coordinate system, and you multiply all these matrices together, that gives you a relationship of stress strain and XY coordinates. So basically, in the code you write, you would start from your fiber orientation, and you define your layer properties. Then you identify these matrices. Okay. So our matrix is this matrix right here. Oops. This is our matrix. It's a utility matrix to go from engineering strain and tensor. And then you get your T matrix, you get your R matrix, which is over here, and you put them all together. And this is the compliance matrix, 1, 2 coordinates. Once you multiply all together, that become a compliance matrix, becomes this matrix in XY coordinates. Okay, we'll do some exercise, but pretty straightforward. You can go back and forth with this. But typically, when your theta is not 0, you have a full matrix. Okay, you don't have a 0 terms. Usually we put a bar on top there to signify it's in a global coordinate system. You have a full matrix that relates the stress and strain in global system together. Okay. All right, so that's the things we end up later using. You know, a bunch of other previous stuff are background materials. We don't really use those. Okay. In calculation, this is a single slide that we use later on. Okay. Just want to point it out. Later on, when you need to look for equations, this few slides is what's important. Any questions? All right. Now micromechanics. Micromechanics with I means small. Micro means small. So we're talking about subject in this scales, fiber matrix. These are indeed very small stuff. Okay. So the utility of micromechanics, you can use these things to predict the average properties of a layer, a lamina, a layer, from the fiber volume fraction, matrix properties, things like that. Particularly material engineers, the guys who make these materials, they can use this to guide their material selection. Let's say they want to achieve certain properties, they select a glass fiber, nylon fiber, Kevlar fiber, carbon fiber. If you know the theory, you can roughly estimate. Let's say you can put in roughly 40% fiber. You can use epoxy-based matrix. Before you really put your hands dirty and really make things, you can estimate pretty close. If you mix these together, make a lamina, what kind of property you're looking at, right? You get a range, pretty good estimation before you even start doing things. So that's what the theory is used for. It's used to allow you to design materials, not quite structures. Structure is another level. When you do structure mechanics, when you do airplane structure analysis, you're at this scale. So we're talking about micromechanics really dealing about this step. It relates the constituent property to the single layer properties. Then you can build up further from there to your big plates and then big structure components. Those are the in the realm of micromechanics. With A means bigger. Okay. Any questions? All right. So the material. This is reference the material that in this presentation I took from these several books. Not a single book. If you're interested, you can get these books. These are classical books. If you look at the background, some of the I didn't sort of label every figures, but I just give you the general reference. Okay. All right. So this is a very nice work published by Daniel, the professor at Northwestern University. He's pretty old now. He's probably retired. So what he showed is the true stress strain. When you talk about material at small scale, you can look at what is the true stress strain distribution at a very small scale. This is basically a photoelastic model of fiber reinforced matrix, polymer matrix under transverse tension. So you have this round circle, that's really strong fiber. And then you have a matrix. When you put in tension, the stress at small scale is really, really non-uniform. The message you get here is at small scale, things are not uniform. Now, when you talk about a stress and bigger scale, you often talk about this lamina is under 300 megapascal tensile stress, maybe. And then you zoom into a smaller scale, that's 300 megapascal. It's not uniformly distributed. Okay. If the material is not homogeneous, you have all kinds of a stress concentration, at the corner of the rounds. So frequently the micro scale stress is an average. When you talk a smaller scale, things get really, really non-uniform. You would call this material inhomogeneous because from point to point there are differences. Okay. Now, this actually affects the true failure mode. The failure mode may initiate from certain regions of high stress, become a bigger crack and propagate, things like that. It can seed a defect. That defect can grow from small micro scale to micro scale. Later on, break a machine. That it actually can start from here. All right. So in the micromechanic analysis, we single out fiber and matrix. We usually separate them out. We think the fiber itself is homogeneous domain. Matrix itself is homogeneous domain. Then we apply series and analytical models to predict average properties. Okay. All right. These are typical properties of fibers. We're talking about 3 representative fibers: a carbon-based material, graphite fiber, a glass-based material, and a polymer fiber. Aramid is polymer fiber. Okay, 3 representative class of fiber. These are the backbone of composites. They're usually used for reinforcement. So you see they are, their modulus, their transverse modulus if you load the other way. So if this is the carbon fiber here, what's matter in this modal loading is the transverse modulus. Is when you load it in the diameter direction of the fiber. Okay, that actually matter. You can see that actually is quite different. The actual modulus is 10 times higher. The transverse modulus is 10 times lower. Can you, based on the material background we learned, can you theorize why there's such a difference? Recall the molecular structure of carbon fiber. Why there's 10 times difference? Can someone give some sort of a reasoning? Does it make sense to you? Why graphite fiber is 10 times stiffer in the actual direction? Think about chemical bond. What kind of chemical bond is involved in the graphite fiber? Covalent bond? Yeah, and only in the actual direction, remember? It's aligned in actual, the way they parallelize and pull together, they align the strong bond in the actual direction. What about if you pull the fiber in transverse direction, what kind of bond you're dealing with? It's a secondary bond. It's the bond between the graphene sheets. That's like it's much weaker bond. That bond is not strong. So basically, this is a fundamental reason why that direction is less stiff, much less stiff than the other direction. Okay. Now you look at the glass; it's the same. The glass is isotropic material. Even at a fiber scale, doesn't matter which direction you pull; it's the same. Okay. Aramid is similarly. Aramid has a long chain polymer. The long chain is a covalent bonded backbone. It's aligned in actual direction. So when you pull the other direction, there's one over force. It's much weaker force. So you look at 8 gigapascal transversely. So the other thing that's highly anisotropic is strength. So similar to the argument, the stiffness is highly anisotropic. The strength is also. The graphite fiber is much stronger when you pull in fiber direction, but if you pull it in the other direction, way worse. Okay. Same thing applied to the aramid fiber. Glass fiber again is isotropic. Okay. All right. So what's the significant is this: when you do the fiber property estimate the laminar properties, it really depends on which direction you're talking about. If you're talking about rule mixture in the fiber direction, you want to estimate the stiffness, you use 230 if you graphite fiber. If you use a rule mixture to estimate the property in the transverse direction, which one do you use? You load it perpendicular to the fiber. If you estimate the property in that direction, use 22. So you don't blindly put a number in. You have to think about which is the right number. It's really depending on the direction you're loading. Okay. Glass fiber doesn't matter. Polymer fiber, graphite fiber, it matters a lot. It gives you very different results. Okay. Polymer, the matrices. Matrices are typically epoxy for carbon fiber. Epoxy is more or less isotropic. You can see this not huge difference in directions. Aluminum roughly isotropic, but much weaker. You see the properties are not same order of magnitude. You're talking about the actual modulus 3.4 gigapascal. Now you look at the fiber, 230. Okay, it's really, this is just a glue, but you really not rely on this to give you a high property. You rely on fiber. This is just bond everything together. Okay. All right. Some of the common metrics when you look at a lamina, the metrics the people often use are these. These are definitions. It's pretty simple terms. One of them, actually, arguably the most important term in carbon fiber composites, fiber volume fraction. The higher, the better. The higher you can squeeze fiber into the matrix, the better the properties. Okay. So definition: if you look at a small volume of composite, you estimate the volume of the fibers and divide it total volume. You got fiber volume fraction. Okay. Fiber weight ratio. If you know the fiber weight ratio, you know the density of each component. You can calculate. They're related. Now, why people know fiber weight ratio? Sometimes when they make material, weighing is easier, so they use weight ratio. Okay. Matrix volume fraction is the complement of fiber volume fraction. If you add matrix volume fraction with fiber volume fraction, you usually get something close to 1, right? Matrix weight ratio, things like that. It's a very simple things. So you can estimate. Now, if you know the weight fraction, you know the density, you can go back and forth. They allow you to, you can really estimate. You can go from one metric to the other. It's very simple stuff. You can watch later. All you need to know is the density of each component. You know the density fiber, density matrix. Then that allow you to basically go from weight fraction to volume fraction back and forth. It's also given here. In this table you're gonna use later to your homeworks. Basically the important thing are these. These are the specific gravity is the density of this material divided by density of water, density of 1. That's specific gravity. Okay. So that's what it is. So this thing is related to density, specific gravity. Okay. Same thing happened here, specific gravity here. Okay. All right. Let's skip these. These are pretty simple stuff. We don't need to waste time on this. You can just talk and talk type of calculation. Go from use density to go from weight fraction to volume fraction, things like that. Let's talk about the packing density. How the fiber can be packed in the lamina. There are different. You can imagine there are different way you can arrange it. If you want to put it in a regular pattern, you can put it in a square lattice, right? You can put it in like everything is sitting on the center of the fiber, sitting on a square matrix, right? Everywhere. And then and you can also put on a hex array. Hex array is, if you look at this 6 is on a hex, right? This 6, that's a hex array. Okay, so this sits in between these two, vice versa. Okay, this turns out to be closer packing. The theoretical packing density of this one, if you squeeze everything together, is lower than this. This is actually higher packing densities. Based on the geometry, distance from fibers, the spacing, you can estimate the fiber volume fraction based on this packing geometry. This is for rectangular packing. This is for square packing. This is for hex packing. Okay. There are upper limits. When you squeeze them together, when the fiber touching, you reach upper limits. You cannot squeeze anymore. Each one has upper limit. For square packing, the maximum is 78.6%. Yeah, that's pretty simple. You just imagine all the fiber are touching now. the matrix are squeezed into the interstitial space between. You cannot go any denser than this anymore. And this is a hex packing when you squeeze everything together. And you can theoretically reach fiber volume fraction 90.7. This is in the ideal world. Nobody can make this high. Percentage wise, it's very difficult. So in the ideal world, 70 is awesome. If you look at someone's fiber, carbon fiber composite, you estimate fiber volume fraction is 70%. That's pretty good number. 40% is what I can make. Slop things together, not pay attention to details, or mediocre process. You look at 40%. This is horrible. You have a lot of resin rich regions. You see the pocket resins; those are the weak pockets. You pull them, the crack will crack up and then propagates. This is much less. See the fiber are much closer. Again, there are some rich region, but much less than this. Okay. This is one important parameter. This will change your material layer property greatly. Your Young's modulus in fiber direction, this one will be much less than this. This is much better. You got more stronger material in it, right? That's making a lot of sense. Okay. Let's see. All right. There are a lot of people have been working on this. I think in the 1960s, very active. When the composite research started, 60s, 70s, 80s, a lot of researchers, professors are actively researching this field. They try to come up with micromechanical models to allow you to relate, fiber and matrix property to the layer properties. They apply all these tools. The tool they use, basic solids, numerical tools. This is a approximation method, empirical method, and then doing experiments. That photoelastic model I showed you before is one of the experimental approach. All of them, what they're trying to achieve is that they want to predict accurately. If you tell them how much fiber, what's the volume fraction, what's the fiber property, what's the matrix, what is the laminar property. All these micromechanic models strive to do that. All right. All right. The most commonly used, the simplest model. Everybody criticized when they publish a model. They say, "Oh, this is a horrible simplification," but turned out to be most widely used. Most people use this, but even though everybody criticized it, I don't know what you. Yeah, these are your workhorse. So basically, depending on which model you choose, the effective properties, it could be Young's modulus, could be shear modulus, is related to a simple rule of mixture. Is the fiber property multiply fiber volume fraction plus matrix property multiply matrix volume fraction. One of them usually give you upper bound, the other one give you a lower bound. Okay. If you plot them theoretically, you vary volume fraction, let's say fiber volume fraction from 0 to 1. So when the fiber volume fraction is 0, you have 100% matrix. Now when the fiber volume fraction is 0, this term drop out. And your matrix volume fraction is 1. VM is 1 because VM and VF add up to 1, right? If one is 0, the other is 1. So you automatically have the effective property equal to the matrix property. So that's a matrix Young's modulus. Both model give you the same number here. Okay. Now you can also check the other end, upper bound. Not upper bound, the other end. When your fiber volume fraction equal to 1, then you have no matrix. We know that's impossible because there are packing limits. The maximum you get is 97%, right? So assume it gets 1. When VF is equal to 1, VM will be 0. This term drops out. So this will be fiber property, EF, right here. And you can prove mathematically. This is always bigger than this. This void model always give you upper bound, and the Rousse model give you lower bound. So your true property is in between these two bounds. If you do experiment, you find these data are sort of scattered in between these two lines. Okay. This is the most widely used. If you know this model, it takes care of most of your estimation needs. Even though there are better models, they're more complicated. But given the simplicity, this is a great tool to use. Yeah, the other name, the most common name, most people call this rule of mixture. Now we learned there are two rule of mixture. One is a void mixture, the other rules mixture. It really depends on which one you choose. It could be either predict upper limit or lower limit of this mixture. Okay. Any questions? At the extreme, at the ends, at the v equal to 0 and 1. In the middle, they don't. All right. These are another approach, the strength of material approach. It just idealization, simplification. So let's say you want to estimate the property of this composite layer. You identify repeating units. You'd argue that you carve out a little bit out of this volume. You can call this thing is a brick, building brick. Repeating everything is can be built by stacking these together, right? These are building blocks. We call that representative volume fraction, or some people call it RVE. And then this thing is hard to analyze because the geometry is not uniform. You can assume the property of this one is equal to this one. Now you actually deform the fiber into a layer of material. This has fiber property. This thing has a matrix property. You just instead of analyzing this cylinder in a brick, you analyze 3 brick together. This step is assumption. It's a simplification assumption. You just boldly assume they're similar, and by doing this, you can analyze easier. You can apply your basic solid mechanics model to predict if you pull a tensile stress in this direction, what is the response, right? This one is harder to do. Okay. All right. If you do this, you can apply. You can give it some geometry. You make sure that the volume of this center disk, center brick, remember that represent the fibers. You give it a fiber property, right? And the other brick, you give it a matrix property, right? Then you apply a stress. Assuming you apply stress in this way, right? In sigma c direction, in this way. And you can estimate what kind of response the material has. So you basically using some argument, the total force, the reaction force from the composite is the sum of reaction force from the fiber, which is this part, and the reaction force from the matrix, right? This is a mechanics equilibrium condition, and you assume the reaction force of the composite is the average stress of composite modified the total cross-section area of the composite. We call this whole thing composites, right? This whole thing is composites, right? So this is your average properties. That's the total area, okay? And then you can separately estimate the reaction force from the fiber and the matrix, right? This will be fiber property, fiber area, matrix property, matrix area. And you plug in an equation over there. All right, so this is the equilibrium, total force, fiber reaction force, matrix reaction force, and then you divide it by total area. And the fiber area over total area is actually equal to fiber volume fraction. This ratio equal to fiber volume fraction. This ratio equal to matrix volume fraction. So this is it turns out that this is basically, do you recognize this? This is rule mixture. This is a void model. Okay. So basically, it says if you make these assumptions, you apply a basic equilibrium, and you can arrive at this void rule mixture. model. Okay. You can apply this to modulus. This is some examples here. Basically, this is a what is that? Glass fiber polymer composites. You have fiber volume ratio varies from 0 to 100%, and then these different lines correspond to different volume fractions. Fiber volume fractions, I guess. You have 0.2%, 0.4%, 0.6, 0.8. The higher the volume fraction, and then you calculate a ratio of fiber reaction force to the composite reaction force. So basically, how much load is carried by the fiber? This is remember when you put the thing, you have reaction force from fiber, you have reaction force from matrix. They actually added together to the total reaction force. Okay. So you can estimate the ratio of them. Okay. So basically, you can see as you go from low volume fraction to high volume fraction, your fiber carried fractional stress go higher. Like that's this trend. Also, there's a trend going this way. When you have a higher volume fraction, then the fiber carries more stress. Okay. All right. So in this case, you have a fiber volume fraction of 70%. Your fiber carries 98% of the force. If you pull the material in that direction, the fiber carries 98% of the force. Okay, the load, which really is what you want to do, right? You want a strong fraction in the matrix, in the composite, to carry most of the load. Okay, this is perfect. All right, any questions? Transverse Young's modulus. Transverse Young's modulus is basically pulling in the direction perpendicular to the fibers. You can prove that when you have a transverse situation, this model works better. The Roos model when you transverse situation. Oops, back. So you apply the Roos. This is a Roos model. This is another rule mixture. Okay. And then you can calculate the transverse Young's modulus composite, which give you this number. It's actually closer to the matrix property. It's slightly bigger than matrix property, much lower than fiber properties. Okay. So basically, if you put a fiber together in a composite like this, you remember the fiber, the strongest direction of the fiber is along the axis fiber, right? So you have huge reinforcement effect if you load in this direction, but you also has a reinforcement effect in the other direction as well. So in this direction, they also make it a little stronger, but not nearly as much as the actual directions. Now, what Roos model tell you, if this is glass fiber matrix polymer composite, your glass material is 85 gigapascal modulus. Your matrix 3.4 gigapascal. If you cut a piece of material, you measure your modulus in this direction, transverse direction, you got 11. It's much different than polymer, but you're not achieving the glass level. The glass is 85, right? So you have a reinforcement going on this direction, property become better, but not nearly as good as the other direction. The other direction, you're almost approaching the glass properties. Okay. All right. Rule of mixture, Roos model. This is experiments. This is basically verification. You measure the actual properties. You make composites, and you make a lamina, and you measure them. You vary the fiber volume fraction, and these are composite properties. These are the rule mixtures. Transverse Young's modulus. The theoretical value of transverse Young's modulus function of fiber volume fraction for boron epoxy. This is boron epoxy. Fibers 414, volume fraction 0.2, matrix 4.14, volume fraction. So these are the data versus model. You can see there's not exactly, it's not really dead on prediction. But order magnitude wise, you're close. You're not really, usually micromechanical model doesn't allow you to, if you get like 1% accuracy, it's impossible. They give you, same order magnitude. Okay. This is the glass fiber. Glass fiber figure. This is not a glass. This is the same thing. Zoom in a little bit for certain range. Actually the Rouge model underestimates. So you can see that all the experiment data points are above the Rouge model. The Rouge model is the model we're talking about, lower bounds. The Rouge model is this green curve. Okay, this curve. Now you may ask, why not using the other model? You can try the other model. The Rouge model is actually closer to the prediction. If you, the other model way over predict. So for transfer, probably Rouge model is closer. You can add a void model. One of them is way higher. In-plane shear modulus. Again, you can basically equivalent. You think of this brick of 3 layers, and then you assume this is approximately represent the composite behavior. You assume one of the brick layer is matrix, the other 2 are fibers, and then you can apply a load to it and see the response. Okay, so this is the equivalent material, imaginary material that you invented. You argue this material, if you load it in shear, it will respond similarly on average to composites. Okay, so you basically apply shear and you try to figure out what's the average shear. You can basically using the layer properties. When you under shear stress, each layer may shear different amounts. Okay, and you can assume that they actually add up. The total shear composite is the sum of the shear of the fiber plus shear of the matrix. Okay. All right, and then obviously it depends on the thickness of material. The total shear, total displacement horizontally due to shear, it depends on the thickness of the layers. The thickness depends on the volume fraction. Okay, you can relate all of them, and you can write the equation. The total displacement is sum of the fiber, sum plus matrix, and then you can predict the shear strain in the composite is this. Shear strain fiber and matrix is this, and you plug these numbers into this equation here, you get these. Basically this basically says the equivalent shear modulus follow Rouge model. This analysis basically shows that it follows Rouge model. It's a rule mixture type. Okay. In-plane shear modulus G12 is related to the shear strength, shear modulus fiber, shear modulus matrix, and volume fraction. This is an example here. Glass fiber, 70% volume fraction. Polymer matrix. This EM is the 3.5 is the epoxy properties, fiber properties. So I want to calculate the in-plane shear modulus using Rouge model. So we need to know the shear modulus of the matrix and then fiber separately. Since the glass fiber is isotropic, you can predict the glass fiber property using this equation. Anybody remember this equation? This is for isotropic material. This equation is only valid for isotropic material. What's the new F in there? What's the new F in there in this model? Poisson ratio. This is Poisson ratio of the fiber. This is Poisson ratio of the matrix. So you can, when this equation is used, you automatically realize that you have applied the assumption that epoxy, matrix, glass fiber are both isotropic. They are indeed isotropic. So you can use these models. So if you know the Young's modulus of the matrix 3.4, you know the Poisson ratio, you can calculate the shear modulus. Shear modulus 1.3, 1.31, right? And the glass fiber is 35. The more you look at the glass fiber property, the more it looks like aluminum. It's almost not too far away from aluminum properties. Anyway, so you get these, and then you plug these GM, GF into this equation, which is a rule mixture equation. This equation right here, this one. And you get a in-plane shear modulus of this lamina with 70% fiber volume fraction. It's very low. It's almost as equal to matrix. Okay. All right. And these are the validations. These are measured. What's this volume fraction? These discrete points are the experimental data. These are the models. Okay. So arguably closer prediction than the other. So you can see here that the utility of these models are you can predict without doing experiments. Experiments usually take a long time, more expensive. You can get pretty close to the real properties before you even mix any material together. It's not that far. Okay. So let me share with you some of the experiences when you want to predict material properties. There are several classes of properties. When you get in the job, people ask you to predict certain material properties of composite, whatever it is. If you're asked to predict modulus means the stiffness or things like that. Usually, it's easy, and you can get pretty close. And then if another day someone asks you to predict the strength, breaking load, it gets difficult. Modulus, if you have tools, you have numerical tools, you have good inputs, you can get into a few percent. You predict match experiment beautifully, usually. For strength, it's way more difficult. Even though you know the strengths of all the constituents, put them together, you predict strengths. Because they introduce a weak interface, all those things, very hard. If you get to like 10, 20, 30%, it's pretty good. Okay, that's excellent job. Usually not very difficult. The difficult level from predicting stiffness to predicting strength is order of magnitude difficult strength. And then another day, your boss asks you to predict fatigue life. That's another level of difficulty. Usually, it's considered magical if you predict number in the same magnitude of experiments. If you're 1,000 cycle, you predict 5,000. It's excellent. Usually, that's another big animal. Can you theorize from a material standpoint why it's so difficult to predict strength and fatigue life? What's the fundamental difference? A lot of people use rule mixture, but there are a lot of different models. But I'll give you some perspective. You set your expectations. When your boss asks you to do this, you set him straight. As you predict fatigue life, you may be a 1 or 2 order magnitude off. So think about the process of these happening. The material deform is a collective property, an average of many atomic bonds deform a little bit. If you do the right averaging, you always get close. Okay. And the failure is really controlled by a few defects. right? If you talk about failure materials, it's a weak interface, a voids, the resin pockets, defective fibers. It's really hard to frame in any analytical models. Very hard. And fatigue is the growth of that defect over a period of time. Okay, it's like predicting revolutions of a society. You know, when this Floyd thing happens, the whole society gets disturbed. Who can predict that? That's like predict fatigue life. You have from a small thing growing to bigger and bigger thing, and you basically, you know, fracture the whole society. That's the fatigue life prediction. I want you to predict from today, how long it take to have another Floyd situation in society. It's really hard. You know, 10 years, 20 years, 100 years, who knows? So that's fatigue life prediction, by the way. Okay. So what we're working on is the simplest of them all. We predict the elastic properties. These are usually get pretty close. In a little bit, I guess we will get into the predictive strengths. Predictive fatigue life is out of the scope. We don't do that for this. All right, so we're basically look at micromechanic approaches. We talk about two approaches really. It's you look at all the approaches available. We basically look at the mechanical material approach. You introduce some highly simplifying assumption. You apply solids models. So you can come up with a model. Usually, it's one form of the rule mixture or the other. Okay, that's the most basic form. And there another form of prediction model is this so-called semi-empirical models. All right, it's just this is a big word, but it's just a guess. Semi-empirical means that it's lucky guess. Okay. I'll show you the models. There's not much reasoning behind it. This is the most famous semi-empirical model, Halpin-Tsai equation. These are the people who invented them. He just said, no, the property of whatever. This is like the Young's modulus, transverse direction, two transverse direction, is dependent on the matrix property plus these bunch of things. These bunch of things are these. Okay. So he came up with a parameter, and then a volume fraction is in the picture. And these parameter you calculate. There's the curves, you fit these. You provide curves. Okay. So basically, this parameter depends on the ratio of these two. Okay. You just use the rules given to estimate this parameters. You stick the parameter in, volume fraction in, you get that property here. Nothing but the empirical equation. But this one works better than most other models. So this is an example, a numerical example. You can calculate using these parameters. So this is a validation of those models. You can see that compared to rule mixture, for transverse property, the Halpin-Tsai equation did much better job. It's almost like curve fitting. Okay. So if you let's say using a code, these models are in sometimes people incorporate it into standard code. You can pick. How do you get your transverse property? You can either enter a number or you estimate. Estimate, they give you options. You estimate the rule mixture or Halpin-Tsai equation. Usually Halpin-Tsai equation give you a much closer guess. Okay. All right. There are more details of this method. This method can be applied to transverse shear as well. It's the same form, almost same form. That's the Hopkins-Tsai equation for transverse Young's modulus. This is the Hopkins-Tsai equation for in-plane shear, G12. It's in a very similar form. Okay. And these parameters, you can estimate the parameters that go into this equation using these empirical equations. It's a curve fit. And you can apply Pocket number in, estimate parameters that goes in, and then bingo, it calculates. This is the comparison of a numerical solution to the estimation. This is the G12, the shear modulus. Okay. Pretty decent prediction. There are no theory behind it. You ask them how they pick the form. There's no reason behind it. They don't care to explain. It's just lucky guess. Okay. I'll give you a set of homework on this. So you basically do some plug and chuck calculation, practice. Now let's talk about strengths. We'll talk about the modulus. Modulus is the easiest prediction. All the fiber direction property are pretty well predicted by Voigt model. The transverse direction properties, you can either use a Roos model or Hopkins-Tsai. Hopkins-Tsai is slightly better than Roos model. Okay. And the easiest predictable property is the fiber direction property. You can predict very accurately. All right, now let's touch upon the prediction of strength. This is the way more difficult task. So basically, what you want to get is 5 parameters. There are 5. You need a 5 strength parameter to, like for metal, you talk about how strong metal is. You basically talk about yield strength, right? A single parameter that give you an overall picture of this thing. For a lamina, you need 5 numbers. The 5 numbers are sigma 1, the tensile strength in one direction. Now, usually one direction is a fiber direction. In this course and many books, by default, 1 is fiber direction, 2 is transverse direction, perpendicular fiber. So you need a number that quantify. If you put a one direction material in one direction tension, this is how strong it is. Is sigma 1, T means tension, ULT means ultimate. Okay. You may ask why there's no yield stress. Why there's no yield stress? Why people don't talk about yield? Because the carbon, the fiber reinforced composite fail brittly. There's no yield. You pull in the fiber direction, they fail like glass. They put boom, boom. No yield. Straight down and boom, fail. Okay. There, you're not talking about yield. There's no yield. Okay. All right. So the other parameter you need to describe the strength of the layer is the sigma 1. C. Guess what C is? C for compression. So usually they are different. The tensile, you put the material in the tension direction and compression direction, they're different. You invoke different failure modes. And hence, there are different strengths. You have a tensile strength, it doesn't mean if you apply the same load on the compression at the same strength. It could be lower, okay? Usually lower, okay? Now, you can pull the material in the 2 directions, which basically that direction is dominated by matrices, right? The polymers. Again, you have a tensile loading and compressive loading. And then you have a shear strength. So there's a minimum set of numbers. You need to describe how strong a lamina is. So you can see this is way more difficult than a isotropic material. You pretty much use single number, okay? Now, you wonder how people get this number. They can do testing. Testing is the most reliable way to get these numbers, which is, I'm in this area. I do a lot of testing for different industries, nuclear, aerospace, automotive, composites, and also tropic materials. I break their material. I try to get these they pay me to do this, but I basically measure these numbers. I give to them they use these for their other models. Okay. All right. So this is a pretty close picture. If you look at the stress strain curve of material failure behavior, this is pretty close. The fiber is usually very brittle, doesn't yield. You just go up linearly to a point, and boom, it break. Matrix, depending on what matrix. Matrix usually sometimes yield a little bit, but there are also brittle matrix. Matrix really depends what kind of it is. Matrix is, as you can see, the slope is much less because matrix is much lower modulus. And the composite you see is in between. It's lower than fiber, higher than matrix, and your failure stress also in between. Whenever the strain level, when the fiber fail, is where usually the composite fail. Okay, that's pretty typical. So the other thing to say is that when you're pulling the material in the fiber direction, the fiber failure defines the layer failure. Fiber is critical in the loading in this direction. Okay. Now, if you make this assumption, the fiber failure strain, when the composite reaches the fiber failure strain, you have a composite failure. You can write an equation to predict the composite strength. You can predict this number. All right, predict this number using the fiber failure properties, and then the composite properties. All right. So this is the fiber failure strain equal to fiber failure stress divided by fiber modulus, right? And the matrix strain is the matrix stress divided by matrix modulus. All right. Then you use a rule mixture that governs how the stress distributed between the fiber matrix. Okay. And you can predict the strength of the lamina if you pull it in the fiber direction. Equal this equation. All right. So you use what you put in there is the fiber properties, sigma f. This is fiber strength, and then your matrix modulus, fiber failure strain, and this whole thing is estimate of the composite failure stress. Okay. And that's how you use it. All right, let's check the units. We should check the units more frequently than this. But any equation that being thrown on the paper, the first thing you can do is check if the units are consistent. If the units are consistent, you don't even bother doing this wrong, right? But you have to have apple equal to apple. So let's see. We have a stress here. With a stress multiply a volume fraction. Volume fraction, no units, right? Is ratio, right? So that makes sense. Now here is a strain value multiply a Young's modulus. What is that? What is that thing then? The stress, okay. And then 1 minus VF, what is that? What unit is that? 1 minus VF? No units, because VF is a ratio, right? No units. So this is no units. So that's good. Stress on the left and stress on the right, right? All right, so this is an example, glass in epoxy, 70% volume fraction. Now these properties actually came from that table that we looked at initially in the beginning of the lecture. By the way, you have this slide on Blackboard. I just uploaded maybe 30 minutes ago. So you pick out the relevant properties out of the table. This is for fibers, modulus, strength, matrix, right? And then you calculate the failure strain of fibers. And then the failure strain of matrix, failure strain of fiber. And then you put everything in according to this equation. And you predict the tensile strength in the fiber direction of this composite is 1104 megapascal. There's an 8 here missing. It's a megapascal. Okay. All right. Again, the reason we can predict this is we made the assumption that the composites has the same failure strain as the fiber. They have same failure strain. Composite fail at a point when the composite reaches the failure strain of the fiber. Okay. Or you argue that the fiber is not stretchable over this limit. Doesn't matter how you embed it. It doesn't stretch over this. If you stretch over this, break. Okay. This is a nice assumption, only for one of the properties, only for this. Another property is not a. You cannot have a single model to cover all. You gotta have other models because the different physical process involved. Okay. This is how you get it. You measure the property using this kind of technique. You put a universal tester. You make your samples. You sometimes put a tab in to help distribute load at the grip, and you measure. You make a standard size, and you pull them. You put a strain gauge on and measure the failure strain, failure load, and things like that. MTS. I have one of these machines. My lab. I have 3-4 other brands. Workhorse of material testing. So how many people use that machine before? You operate this machine? You use it? MTS? In a Magnair? Okay. All right. Very good. Motor failure. So this is sometimes people look at these, look at basically the fractography of the cross-section area to give you some ideas where the weaknesses are. One of the things I want to point out is this kind of fiber pullout. Okay. This is a very important feature for a class of material called ceramic fiber matrix composites. When they see this two type of failure, they would re-engineer the material. When they see this type of failure, they are happy. The reason is that when you have these fiber pullout, you actually have a lot of energy dissipation associated with it. That creates the pseudo toughness. The material become apparently tougher when the material fails. There are a lot of these occurring. They dissipate energy. They dissipate a lot of energy out of this. So when you have this kind of failure, it's usually it's a brittle behavior. This is a more tougher. Remember, the toughness of material is energy you put in to break material into two, right? The energy is not stress under the curve, area under the curve, stress rating curve. So if you don't have a fiber pull out, usually the area under the curve is very little. When you have this kind of a phenomena, fiber pull out occurring, correspondingly, you'll see bigger area under the curve, okay? Which is desirable to make a tougher material. Thermal expansion, matrix property. I think this is I don't know where this come here. So you can use rule mixture to predict thermal properties, thermal expansion coefficient. So polymer expands a lot more than metal or ceramics. So this is means that you when you have certain temperature change, you have actual contraction. Your fiber contracts in actual direction, but expands in the transverse direction. Okay. Glass fiber expands uniformly, and aramid fiber similar carbon fiber. It just contracts one direction, expands the other direction. Okay. And the epoxy, the polymer expands a lot more than the fibers. The epoxy expands a whole lot more in epoxy isotropic, aluminum isotropic, polyimide isotropic. You see the order of magnitude difference, fibers and matrix. Oops. This is a fiber. The number are smaller, and this is a matrix, much higher. What is the steel? Anybody know what the steel thermal expansion is, roughly? What is the thermal expansion? It's a good idea to pick a set of material, get familiarized, and you have baseline when you compare the material. Steel is between 10 and 20, somewhere, depending on what kind of steel. Stainless steel maybe a little less, 12, 13, 14. So you can see that these epoxy are way bigger. These are huge numbers in terms of, and this is less. This is all less than 10. See, all this magnitude less than 10. Okay. Now these are micrometer per meter. Some people use ppm. Why is it ppm? A lot of people say thermal expansion is 10 ppm per degree C. Now, is that the same unit as this or different units? When you say, what is the 1 micrometer per meter? Make a guess. Now, if you have a bar of 1 meter long, you measure the length, then you raise the temperature 1 degree C, the bar grow 1 micrometer. That's what it means. Now, what's the 1 micrometer compared to a meter? Yeah, that's right. 1 micrometer, 10 to the minus 6 meter. So it's a 1 millionth of a meter. So that's the 1 ppm. 1 micrometer per meter is 1 parts per million in terms of elongation. So when people talk about ppm or micrometer, they're talking about the same thing. Okay. All right, so this is the thermal expansion in the fiber direction, matrix direction. The prediction equation based on rule mixtures. You basically look up the input to it, which is the fiber property, matrix property, Young's modulus, volume fraction that goes in, like these. This equation is for fiber direction. This is for matrix direction. Some derivations. Are we out of time? What's the? I see some people. What time is it? Okay. All right. This is the what is this? This is one of the mechanics models predicting free expansion of a freestanding material that involves some fiber matrix. So the argument made is when you have a fiber freestanding material, there are no stress applied to it. So applied stress is 0, but there is internal stress because the fiber matrix expanding different amount, they fight each other. You have some fiber stress and matrix stress, but they balance out. They add up to 0 because there are no external applied force. They internally balance. So you can write this equation. Fiber stress times volume fraction fibers, matrix stress, volume fraction matrix, you add as 0. This is a sort of a self-equilibrium. This is nothing but equilibrium, if you think about it. That's the equilibrium equation. And then you plug in the property in. This is how you express the fiber stress based on the thermal expansion and Young's modulus. Okay. This is a stress for matrix. And you plug them in, you can predict the composite in one direction. What is the composite strain when you have a delta T? Okay. So this is the final equation. You basically have fiber property, matrix property, volume fraction, fiber, volume fraction, matrix, all combined together. And this is a parameter that you can predict pretty accurately. This is comparable to like a stiffness prediction. This is one of the easy predictions. Okay. Transverse. This is a case for transverse thermal expansion. E2. Similar argument with an example here. You can read them later, but this is a sort of a parametric plots and experiments measurement. So long story short, you can predict pretty accurately. It's almost right on the model and prediction. All right, I'm gonna stop here. They're about half. They're about of. You can start. I mean, you're still working on string homework. This is another homework coming up, but you can leave this for now. But later on, this is another homework that's coming up for predicting properties. Okay, I'm gonna stop here. I'll see you guys Wednesday.